In section 5.1, we looked at redefining the natural log using integrals. And based with that new definition of the natural log, we looked at how to do derivatives involving the natural log. In this section, we're going to go the other way and look at integration with the natural log function. So we'll use the log rule for integration, and we will look at the other trig functions, because we have derivatives, or we have integrals for sine and cosine, and we have it for, tangent squared and secant tangent, because we have ones that came out of the derivatives. We're going to look on finding the integrals of your other basic trig functions. So coming back to kind of where we left off, the integral of 1 over x dx is going to be the natural log of the absolute value of x plus c. And the integral of 1 over u du is going to be the natural log of the absolute value of u plus c. That's why we define the natural log, in order to be able to differentiate this 1 over x. And we can come along with this one, because if we say, really we're looking at that substitution, and we have u prime over u dx, and du is u prime dx, so that's why we can make that just 1 over u du. So we're really working with that substitution method when we do this. So let's look at a few examples. And again, try these on your own, see what you can do, and pause the video, or work through one example with me and then try to do the own. Kind of jump back and forth and see what we can do with these. Really, it works best if you're trying to do this on your own. You know that, right? Yeah. So this first one is pretty straightforward. We have a constant multiple here, so we can make this 2 times the integral of 1 over x dx. And that's straight from our definition. That's 2 times the natural log of the absolute value of x. But here's the one nice thing. We got this right. The absolute values, I hate using those if I can avoid them. But we have this multiple of 2 here. We can use our properties of logarithms in this case to make this a natural log and square this. And when I square it, it doesn't matter what it is, so I can get rid of the absolute value, because squaring is going to make it positive. So I could maybe rewrite it that way if I don't want to have that absolute value in there. So on this next one, this is a, 1 over a function. So we got to think again and say, well, u is going to be 4x minus 1. du is going to be 4 dx. So dx is du over 4. So we got to look at that, because we don't have u prime over u. But now we can take this as the integral of 1 over u times du over 4, or 1/4 the integral of 1 over u du, which is 1/4 the natural log of the absolute value of u, which is 4x minus 1. On this one, again, we got a whole lot going on, but if I make u be x squared plus 2x, du is going to be 2x plus 2 dx. Whoops. Let's fix that. And this has a common value of 2, so if I can pull out, I can make that 2, say du over 2 equals x plus 1 dx, which is what I have right here. So I can again say, well, I got that constant of 1/2. I'll take that out. That's 1/2 the integral of 1 over u du, which is 1/2 the natural log of u plus c. I'll put that step in there. So that's going to be 1/2 the natural log of x squared plus 2x plus c. Now in this case, I'm not going to take this in because, yeah, taking the square root, that doesn't help anybody, right? Okay, maybe it does. Who can say? So for this last one, again, come along, u, x cubed plus x. So du is going to be 3x squared plus 1 dx, which we already have that in there. So we again get that integral of 1 over u du. So that is just going to be the natural log of, oh, I'll write it all out. Natural log of u plus c, or the natural log of 3x squared plus 1 plus c. But again, if I look at this, x squared is always positive times 3 plus 1 is always positive, so I don't actually need the absolute value in this one. So I can write it like this and get rid of my absolute value if I want to do that. No, I can't. Sorry. I'm making errors when I'm doing this, so I pulled in the wrong thing. Correct me when I mess up badly like that. Well, yeah, you can. I know, you're shouting at me. Okay, maybe not. Because u is not 3x squared plus 1. That's d. That's the derivative. So this should be x cubed plus x. That's much better. So again, main reason we came up with this natural log is in order to be able to deal with that integral of 1 over x. Now, when we look at this one, I got x squared and I have x squared. So I'm not going to have the derivative of x squared in here because I got an x squared as well. So I got some problems. So sometimes we're dealing with fractions, sometimes division will help us. So if we look at this if we divide this out, x squared plus x plus 1, I can't do this synthetic because I got an x squared here. But it's a pretty straightforward one. X squared goes into x squared once. So we got 1 times x squared plus 1 is x squared plus 1. We subtract that and we get x. So we have a remainder of x over x squared plus 1. So now we can rewrite this interval and say that's the integral of 1 plus x over x squared plus 1 dx, which I can make that the integral of 1 dx. I like that one. Plus the integral of x over x squared plus 1 dx. And on this one, again, we can go u is x squared plus 1. So du is 2x dx. So we want du over 2 to give us x dx, which is what we need there. So we get the integral of 1 dx plus the integral of 1 over u, 1/2, 1 over u du. Can they be different variables? Yeah, they're different integrals. I don't care. So the integral of 1 dx is just going to be x plus c. Here we're going to have 1/2 the natural log of u which is x squared plus 1. And then I can add c to it. Now, that's the one I was meaning to talk about earlier, where I can say, you know, x squared plus 1 is always positive, so I could write this as x plus 1/2 the natural log of x squared plus 1 plus c. Doesn't really matter. Now we come to this one. And again, here I have a composite function down here. And if I wanted to make this 1 over u, well, I'd have to multiply this out, and the derivative's not in here. Play some other games. But we're going to substitute in here again. Oops, let's go back. And then if we let u equal x plus 1, du is going to be just going to be equal to dx. So that takes care of the dx, that takes care of the x plus 1. I still have this x here to take care of. So I'm going to re-look at this and say x equals u minus 1. So that breaks this down. When I do this substitution in, I get the integral of 2 times u minus 1 over u squared du. Well, what can I do with that? Here's a constant I can pull out. And again, well, here the derivative of that is u, but that minus 1 messes me up. But I'm dividing by a monomial denominator, so I can just break that up. 2 times, we got the interval of u over u squared du minus the integral of 1 over u squared du, which we can relook at that. Let's make it, whoa, I didn't want to do that. Let's make it a 3, no. This is just 1 over u du. That's one easy to deal with. This is u to the negative 2 du. Again, that's easy to deal with. Here we have 1 natural log of the absolute value of u. Here we have u to the negative 2, so we're going to u plus a negative 2 plus 1 is a negative 1 over a negative 1. And then I'll just add my c on the end. So we get 2 times, let's go 2 natural log of u. Well, u was x plus 1. Minus, this is u plus minus a negative. We got 1 over u, so 1 over u, which is x plus 1. Except we multiplied it by 2, so we'll put 2 over x plus 1. And then we will add a c on there. And if you really want, we can do this trick here with this 2, and we could also make this the natural log of x plus 1 squared plus 2 over x plus 1 plus c, because we could get rid of the absolute value by bringing that square in if you wanted to. You don't have to. So, again, more tricks we can play with this. It starts getting more and more confusing as we're looking at this. So basically, here's some guidelines you can use when you're trying to integrate a function. Know those basic antiderivatives that we have. We have 12 formulas, power rule, log rule. We have those trigonometric identities we've done so far. If that works, awesome, you're ready to go. If not, look for part that resembles what you have and see if you can use a choice of u, do a u substitution to make that work. So otherwise, try playing with that. Can you simplify it? If it's with trig, can you use a trig identity? Can you use multiplication, division by the same quantity, add, subtract? Can you rewrite what's in that integrand so that it's a way you have a way to look at it? That's where you have to be creative. The more things you know, the better your algebra skills are, better you can do that. All else fails. There's ways to do it. Computer softwares, there's ways to get that with technology if we need to. So I want to finish off with the trig functions. So what do we do with the tangent of x? Clear off this junk. Oops, we got tangent and secant here. For some reason when I went to there, oh well, who cares? Tangent's not too bad here. Because tangent, if we rewrite this as sine over cosine, and then you say, well, if u equals the cosine of x, du equals the opposite of the sine, dx, so we can say dx equals, or the sine of x dx equals the opposite of du. Either way, we can write this as the integral, the opposite of the integral of 1 over u du. So that's the opposite of sorry, I'm messing. Okay, that's the opposite of the natural log of the absolute value of cosine. So the integral of tangent is the opposite of the natural log of cosine. Secant isn't as nice. Secant is 1, if we could rewrite this as 1 over cosine. But again, it's 1 over a function, and we don't have the derivative. It's not u prime over u, so this doesn't help us at all. So we're going to do one of these tricks that who knows how you could come up with this on your own. So I'm going to tell you, this is the trick you do. We looked at this back earlier when we were looking at trying to do some things with these trig functions. If we multiply by 1, this is where the creativity comes in. Secant plus tangent over secant plus tangent. Why in the world would we do that, Mr. Wilkin? Right, that sounds like a stupid thing to do, because it works out really sweet. Because that's going to be secant squared x plus secant x tangent x over secant x plus tangent x. But if you make u equals secant x plus tangent x, du, the derivative of secant, is secant tangent. We have it right here. The derivative of tangent is secant squared. We have it right here. So if we can make that our denominator, this is now our derivative of our denominator. I forgot my dx here. And that turns into the integral of 1 over u du. So that's just the natural log of the absolute value of u, which is secant x plus tangent x, plus your constant. You can use a similar trick to do cosecant. Cotangent works just as slick as tangent. So I will just give you them right here. And these are the rest of our integrals of trig functions that you can work with. So got some more antiderivatives. Yay, right? So I'm going to leave you with this. Those of you that are my students, you can get this is just a fun video on YouTube summing up calculus. It's on the slideshow, those of you that have that. For those of you that aren't my students, I will link the link to this video in my comments so that you can watch this as well if you want to have a little fun with music and calculus.